Hey students, it's Paul here, and we're going to look at the algorithms quiz homework assignment we had. And of course, question 1, did you watch the video? And I'm sure the answer for that one is going to be yes. So we can put it right there. That's good. All right, next one. What are the, let me switch over to Control W, Control S. There we go. What are some types of algorithms that fit the description in the video? So note this is the description that fit the description, not just ones that were in it. So first answer here, let's look at these guys. I can see this is an important note. Whenever you see a question on here, all of the above is one of the options. So find items in the grocery store. Yep, that one was definitely in the video. Decide what I want to do after school. This looks like a decision. It could be a process. You could have steps to solve the tasks. So that one could be an answer. Select the next move in a chess game. Definitely a process. Do I want to lose a pawn or a queen? So I could continue down this list, but since all of the above is one, we know that's going to be the answer here. So that's the answer. We don't need to dwell on that anymore. Anytime you see all of the above, always make sure to look at a few of them. Describe an algorithm to find items in a grocery store. That was one that was in the video. A lot of you got that just right. The important parts here is you should see that your solution needs to move from a very broad problem to a narrower problem. So it's like figuring out what aisle, figuring out where in the aisle, and getting the product. Now, some creative answers to that would be ask the manager, go online, pick it, have it delivered. Those would be some creative answers to it. But it all has to do with something with mapping everything the store has down to what you want. So that would be that answer there. Next one. For an algorithm to be good, does it have to always come up with the best answer? And the answer to this one here is no. Sometimes good is good enough. And there's lots of questions. Think about questions throughout the day. Like, what am I going to have for lunch? Well, is there a precise answer to that? Well, it should be good. It should be food that's good. But as long as it fits a narrow, a window in that, it's going to be okay. The classic example, which was in the video, was figuring out how to map a route. For visiting a lot of places, UPS, FedEx do it every day. You'll do it when you drive. The point is that things could change. So computers can solve things with precision, but not. The key word here is any. And it's like, nope. So it's definitely not any problem. They cannot do that. All right, next one. Why do some algorithms only look for good enough answers? Look at this. Clue here. Gave you these, all of the above is a possibility. So a provable perfect answer would take too long. That's common things. Computers could, some problems can literally take billions of years or longer. So that's not going to work. Or to use too much memory. So that's definitely the case. The algorithm may have only access to some of the data. That's right. So if you're going to do that map of where you want to go, you don't know what the traffic's going to be like later on in the day. And that's part of it there. May change as it goes. So the answer to this one would have been, this guy right here. That guy. Okay. So, but you got that one. We'll go back to the next one. All right, answer P. Why is this clicking on that here? Click. There we go. All right, describe an algorithm that usually ends up good enough. The classic one here was a pathfinding algorithm. And in this video, the answer here was there were 25 trucks. So I'm glad. I think a lot of you guys got that right. So that means you did watch the video. Good sign. Okay, the next thing we were looking at was the Minesweeper game. And I know some of you have gotten it to run. A few of you just downloaded it. It's really simple code. I'll show that in another video. But the core of it is it's a simple game. It came out, it was mainly popularized in Windows 3.1. I'm going to go fire up tile of it right here. Basic model is you've got a board, so it's like a board game, but you don't have to play anybody else. You can play it yourself, so it's a form of solitaire. And you click a square and it says, there's a mine somewhere nearby, but I don't know which one it is. Could it be this guy? No, this guy. Oh, boom, that was it. It was this one. So now that I know that that was a mine, I can click all the rest of them here because I know that they won't be mines. So the goal of the game, and I've just lost this one pretty bad, is to clear out everything that isn't a mine. And when you find things that you're pretty sure are mine, and I'm going to do that like right here, I can put these little flags and say, watch out, there's not going to be one. So it's a very simple game, as a lot of solitaire games are. And that's what we're playing on here. So I'll set that aside. So just that setup, and all the questions that we're going to deal with in the next few are a 20 by 20 board, and it has 25 mines. And it's beautiful software. You can just change that parameter. You make it a 10 by 10, 20 by 20. You don't have to go to the store and buy a new one, or go online and order a new one. Either way. Okay, so this is an example of algorithms we're going to use to set that board up. So, you know, the programs we've done so far have just been like, say, you take the turtle graphics. Okay, just draw a line, turn, draw a line, turn, draw a line, turn. And you repeat that over and over and over again. And it makes a nice picture. But it didn't really, so it did a task, and we took steps. So there is an algorithm for drawing that picture, but it's not an algorithm for finding an answer. And that's a part where we're really shifting now, is we're going to turn into code that tries to find answers. If you want to get something in the store, that's a set of steps to find a solution, to find the product you're looking at. So you're looking for things, searching for things, trying to find things. It's a new twist. And early computers, that wasn't, a lot of the computers about automating something, just doing something over and over and over again. And there were ones, calculators, like sextants, looking at the sky, trying to figure out where the planets are, where you are a ship on there. You're finding an answer there. But the math was very, very simple. It wasn't searching through something, and that's what we're doing now. So, if you're going to play this game, you're going to have to set up this board. And there's going to be a data structure, like a two-dimensional array, or in Python, we just basically say it's a list of lists. The outer list is a set of rows, and so this is the first row across the top, then the second row, then the second row. I can show you right here like that. So these would be the rows. And then you have the columns. So then the columns are like that. That's the way you talk about the description of it. All right. So it's going to have to do a few things. We're going to have to place the mines, and then we're going to have to figure out these numbers that go in each one of these cells. And then we're going to hide them all. So when the user begins to unveil them, we'll find out what number we should show. Or if they click on a landmine, it's going to go boom. So one of the steps, and we're going to look at two of them here, one for placing the mines and one for actually calculating the numbers. We're actually going to look at the counting the numbers first. So suppose we have this board, and this is list of lists. It's going to have 20 rows, and each row is going to have 20 entries for the 20 columns. And over there, somewhere in there, 25 of those entries in that two-dimensional structure are going to have a mine, and it's going to be marked with a capital M inside that variable. I didn't actually say that in the question, so some of you might not figure that out the first time around, and I should have added that. But it matches the code that you've seen, so I'm going to presume, at least from now on, you'll grasp that. If I had the comment in here, that'd be clearer. So question 1. Here's an approach to initialize the game board. How many times does it have to do a particular computation and for this grid? And the point of this is, when we're looking at algorithms and we're measuring their efficiency and their accuracy, one of the things is just to understand how it works. And so here we're looking at, what we're going to do is, like, if I'm looking at a square, for example, this one right here. Suppose I'm in this guy right here. Okay, there. Like that mine. I'm trying to figure out, well, how many mines are around it? And so I figure out the ones and the twos. So, all right. So there's two loops here. So you get used to reading code. Big thing. Always find the loops. See where they are and see what loops are nested. And this one's actually got 3. So if you're doing any homework assignment, or you're doing a test online, when you're looking at some code and it's asking questions, right off the bat, just mark the loops so you know what's going on. All right, this one says for y in range, and this is basically for each row. And then for each row, we're going to look at each column. And in the end, we're going to look at each cell, and we're going to see if that cell, what it has in it. And it says, if this grid does not have an M. Well, okay. At this point, you should do that right up front. But at this point, don't go too much farther, because there's an awful lot of just silly stuff in here. We don't know what in the world that is. Better go read that question. For the 20 by 20 grid with 25 mines, how many times will line 4 be executed? So let's go look at that. Line 4, that's right here. Where my little arrow? There's line 4. Okay, that's the if clause. The question's not saying how many times is the if true, it's just asking how many times this if is going to be asked. And so we're in 20 by 20 matrix. So 20 by 20 is 400. So let's see. Oh, look, there it is. 400. So 400 would be the answer. All right, next question. Looking at the same algorithm, I did copy and paste it for both of you, but it is the same. And so because of that, you can presume I didn't trick you on anything. Line 5 is inside the if statement. So this is this was the if. Now we're, whoops. This is line 5 right here. This is inside the if. So for the same setup, 20 by 20 with 25 mines, how many times will line 5 execute? So inside here, the key logic is if grid not equal to m. So how many cells won't have a mine? And if it's 400, that means it would be 400 minus the ones that do have mines. So that answer for that one should be 375. All right. Oh, I'm looking at my timer right in here. Control X. There we go. All right. Next one. Taking this function one step further, the inner block of lines 15 through 13, or 5 through 13, builds a list of the 8 possible neighbors for a cell and then iterates through them. You know, what are these neighbors? So this is a part here. It says neighbors right there. How many times will the try statement on line 9? That's right here. We haven't used a, whoops. You know, if I click on this the right way, it goes away. There we go. Oh, wait, it showed you the answer. Well, we'll explain it real quickly. Let's look at those neighbors for a second. I have a slide right here. So in this algorithm, there's going to be a cell we're looking at. The first one will be row 1, column 1, or at index 0, 0. And so the first cell, and we don't know what's in there, but we look at its neighbors. And so we look at the neighbors and we have to count them up. And we have to, well, no, we don't count how many neighbors it has. We count how many neighbors have a mine in them. And because the algorithm is building the board, it knows, it can see the pieces behind it. But right in this picture, you don't. Now note that some of them aren't there, because in the top one, when it's 0, 0, some of the indexes, this would be like, this one up here at the top, like this picture right there, that would be index -1, -1. And like, well, that doesn't make sense. We'll talk about that in a second. And the one on the bottom also has ones that are wrong. But each cell, in our big game, there's 400 of them. Each one will visit 8 neighbors in some form or fashion to see if there's any mines. So let's go back and look at that code. All right, so the 8 by 8, how many times will the try statement on line execute? And so this try is going to execute 20 by 20, to look at the code right here. It's going to be 20 by 20 minus the 25. And then since it's 8 neighbors, and we do this try for each one of the neighbors, times 8. So the answer is the 3,000. You know, when I do this test again, I'm going to change the size of the board, so the numbers won't be exactly the same. All right, which sentence best describes the algorithm used in the last 2 questions? So looking at, I can see that there's a lot of commonality, but so for every cell that is not a mine, the count is the sum of how many mines are next to it. For every cell that is a mine, okay, so this is the key word here. I'm trying to explain what's going on. Is a mine versus is not a mine. And this random stuff, yeah, it's like, whatever. I just threw that one in just for fun. Because there's no random call in the function, so it couldn't be that one. So in this one here, back to this answer, it's right there. Is not. That not equal to m. So the questions are pretty straightforward. So now we haven't used try except. It's called exception handling. It's a whole area in Python and Java and C++. Lots of languages have that. We haven't touched it, but you don't really need to know what it does to answer this question if you just use reason about it. So what error is this code trying to catch? Well, let's see. Clicking on a mine. I'm going to look at each one of these. Clicking on a mine. Well, there's no mouse function related. It has nothing to do with clicking. And clicking on a mine, well, I guess in some it's sort of an error, but it's not a programming error. It's like a user playing the game error. So I don't think so. So it's not that guy. Dividing by 0. But in this try, in this code here, nowhere in here is there a division. So nope, not divide by 0. It's a different piece. So we can guess it's this, but let's look at the answer. Let's look at what it says. Indexing a list beyond its length. And it's like, well, shoot, we're indexing, so maybe. In fact, what that's trying to protect us from is exactly this. So when we're right there, I'm going to clear off that screen. There. It's these particular set right there. Those would be indexed off the edge. And in Python, if I index a list beyond its length, it will throw an exception. And if I don't have a try except, the program will just crash and everything will stop. And that's not good. All right. Now, move into the next one. So yeah, so the answer to this one is this guy right there. Okay. Now, when we took that initial code, and that's what I first got, I said, this isn't the best way to do this. And we don't have to do it the best way, but I want you to learn. I want you to see the contrast between the two, and I want you to see it and evaluate it partly for yourself. So in this case, the loop for initializing is much the same. We do have the 2 for loops. We don't have an inner loop for neighbors. That is somewhat handled inside of this, but by taking that and putting it in a subfunction, that's a first piece of code style, is you don't want too many levels of nesting in a program. So we'll just take that out and put it inside of here. The second part is very subtle, but it's like we're doing equals to mine instead of not equals to mine. And that's what this question relates to. How many times will line 7 be executed? And that's the line right here. I could put arrows to highlight it just for you, but I figure you should be able to see the number 7 and relate it to this number 7. That's part of the nature of growing up and getting ready for college, is to be able to infer some of that stuff. So this is a simple. Rows times columns is 20 by 20 is 400. So that's that one. Same answer as last time. Looking at the same algorithm with the 2020 with 25 mines, how many times will line 8 execute? And here's the difference. Remember the other one, we looked at everything that wasn't a mine. So that was 375. This one says if grid RC is equal to a mine, and since we only have 25 mines, the answer to this one must be 25. So this algorithm, the 2 different ones, the inner loop, instead of doing something 375 times, I did it 25 times. And that usually means faster. Doesn't always. But it's kind of like saying, if I'm trying to find 10 people in Austin, and I could visit everybody who's not those 10 people, or I could visit those 10 people. And it's a little exaggeration there. What sentence best describes the algorithm used in this last 2 loops? Well, I gave you the exact same questions as before. So the real choice is for every cell that is not a mine versus every is a mine. In this case, it's the is a mine because it was equal to, it was the equal right there. Right there, it's that equal. So the answer to that one is this one right there. Okay, now, placing the mines. Okay, that's right, we're in section 303. I'm gonna go ahead and stop this video and pick it up on the next one. We'll close it out in the second part.